Welcome everybody, and welcome to all of you who are tuning in on the video cast. So a few updates, and I'll try to be brief. First of all, we'd love to welcome our newest member, Dr. Mala Murthy from Princeton University. Mala is a professor of neuroscience, and her research focuses on the neural mechanisms and computations underlying social communication in Drosophila. And she's also been quite active in the Drosophila Connectome project as well. And again, as Kara mentioned earlier, she is one of our at-large MCWG members, and we're really looking forward to working with Mala. She's really going to be a great addition, I'm sure. Another update, I work with a terrific team of scientists in the Office of the Brain Director, and I'm delighted to let everyone here know that as of March 2021, Dr. Andrea Beckel-Michener at NIMH was officially named the Deputy Director of the NIH Brain Initiative. And it's really been wonderful working with Andrea, and I really look forward to many, many more years of working with her and the rest of the team as we move forward. As many of you know, the science in the NIH Brain Initiative is organized around 8 project teams, and these are the terrific folks who make things happen together with their team members who hail from 10 NIH ICs as well as Office of the Director. And I really just want to pause and give great thanks to all the great work that all these people do. COVID has been terrible, but the pandemic has brought out the very best in each and every one of these people. And I really do appreciate all that they put in spite of the many hardships, personal and professional, that we are all enduring. I have a new webpage, so you can go to the Brain Initiative website, and we now have a Director's Corner where we will be updating the community with what's going on in the Brain Initiative, discuss issues, topics of the moment, as well as to give people a preview of some coming attractions. So tune in on that. We'll try not to spam you too often, but this is a good place to get information in addition to the Brain Update blog. Okay, so where are we? We're in midway through fiscal year 21. We're very fortunate that Congress gave us an additional $100 million in appropriations over FY20. So our budget for this year is $560 million. And again, for those of you who are a little bit less familiar, BRAIN's funding comes from 2 main sources. My mouse is jumpy, sorry. Base funding that goes into the 10 NIH ICs. Right now it's sitting at $460 million, on top of which we are very fortunate to have received significant funding from the 21st Century Cures Act, which adds a variable amount of funds from year to year. So here we have an additional $100 million, which brings us to $560 million for FY21, a bit more in 22, and a lot more in FY23. So as many of you may recall, we have used this very generous funding, especially this big increase in 2023, to stage 3 large projects that we feel will transform the way we conduct neuroscience research and ultimately have an impact on human health. The first of these was launched was the Resources for Brain Cell Type Access and Manipulation Across Species. This is the so-called cell type specific armamentarium. This has developed tools for cell access in rodent and non-human primate brains, other organisms, and including human cells and tissue. And the long-term goal here is to develop therapeutic strategies for human brain disorders, namely gene therapy and related therapies. The first 2 RFAs are already out. The first has already, we've already had 1 receipt date, another one in October for developing scalable technologies. And this RFA MH21-180, which has a receipt date in November 2021, is for standing up production facilities, specifically in partnership with minority serving and idea state institutions. We are also about to launch the phase 3 of the Brain Cell Census Project, or the PARTS list. This will build on the success of the work that's been going on in their Brain Initiative Cell Census Network, or BICCN. Again, the shift will be to emphasize work in humans to stand up a comprehensive human brain cell atlas. We've just published the so-called notices of intent to publish funding opportunity announcements. There will be 3 FOAs published later sometime in the summer, with receipt dates of November 2021. Now, both of these projects have received congressionally directed funds that will allow us to accelerate the launch along these timelines. And finally, we've been working on scaling toward a whole brain microconnectivity analysis or wiring diagram. This will be to generate a high resolution connectivity map of an entire mammalian brain or brains at multiple scales. We just finished a 5-workshop series this spring. There'll be a workshop series report coming soon, and we'll make sure that you all can see that and hopefully give us some constructive input on that. But this is a project that we will be looking towards standing up over the coming year or two. Okay, a few other things going on in brain. This commercializing innovation, concept to clinic commercializing innovation or C3I program, which is a pilot program to help investigators with an idea of their technology to bring to market, to assist them in shaping those ideas to give them better chances of success. This has been ongoing through NIBIB. We've signed on to this. Applications are due soon, May 25th. Any questions, let us know. This will be exciting to see and is really in line with Brain's mission to disseminate the technologies that we develop to get things into other people's hands and ultimately into the clinic where applicable. So we have several upcoming events. NIH there's a trans-NIH initiative called Bridge to Artificial Intelligence or Bridge to AI, a common fund program, and this is to help to build AI more into the fabric of what we do at NIH. So information on that will be coming. We will be hosting a circuit therapies workshop in late June as well. And this is really looking ahead towards seeing what the opportunities are for developing circuit therapies with an emphasis on gene therapies, but there'll be other modalities, I believe, included as well. And then last but certainly not least, our Brain Initiative Investigators Meeting, the 7th annual and second virtual investigators meeting will be held June 15th through 17th. I just want to stress that everybody who wants to participate is welcome to. You do not have to have brain funding. Registration will be open up through the first day of the meeting, and you can get more information at the website indicated at the very bottom. So here I'd just like to take a few minutes to talk about some recent studies that have been published, and these are all literally hot off the press. I'll try to go through these quickly, but each of these is really represents quite a bit of effort. The first I'll talk about is a study from David Kleinfeld and Rui Costa's group, who conducted a multimodal analysis of parvalbumin neuron output neurons in the basal ganglia's substantia nigra pars reticulata. So these are the set of major output neurons, and they found that that these neurons project to over 40 sites in the brainstem and diencephalon, and the neuronal subsets displayed. Each of these subsets that projected to different areas displayed distinct electrophysiological as well as topographical properties. So there seems to be they were able to correlate these different properties across the different modalities. And the very interesting finding was that these neurons projecting to the brainstem nuclei also sent collaterals to the diencephalon. So they're both projecting down, as it were, as well as up. So this kind of, I think, shapes ideas about how these neurons might play a role in linking these higher and lower brain regions. And it has implications given the role of the basal ganglia and the substantia nigra pars reticulata in neurologic and neuropsychiatric disorders involving brainstem function. So this paper just came out a little bit earlier this spring, a real technical tour de force, very comprehensive analysis, and I'm sure will serve as a great resource for people trying to investigate the basal ganglia's role in these different functions. Okay, literally smoking hot off the press, a paper from Honghui Zheng's group from the Allen Institute was published, I believe, in Cell, I believe, on Monday, where they sequenced over 1.3 million cells from the mouse isocortex and hippocampal formation. They identified over 350 cell types. I put this in quotes because it's really kind of an operational or definition at this point. And they found some interesting things. The cortex and the hippocampal formation share most GABAergic cell types. So here on the right, I show you, they just indicated the regions that they analyzed by single cell transcriptomics. So the regions from the isocortex are mainly in these warm colors, from the hippocampal formation in green. Here you can see these 350 some odd cell types they identified statistically. And in this second row here shows the origin of these cells, either from warm from cortex or green from hippocampus. Over on the right here are the GABAergic neurons. You can see that the GABAergic neurons comprise both cells from both regions, whereas there's greater specificity in the glutamatergic neurons. And there are, of course, specializations for both regions as well. They see a parallel cell type and lamina organization between cortex and hippocampus. So even though these cells are distinct, they're actually showing common properties and common levels of organization. And the interesting thing is if they look in both cortical IT neurons in particular, but also throughout the hippocampal formation, they can observe a continuous variation. And this echoes previous studies by Spruceton and others, as well as work from Hongquei's group, as well as from Andreas Tolles' group. So this is really quite a technical tour de force. I recommend you take a look at it. I don't recommend you try to read it all in one sitting. It's really quite a lot of information. And again, will serve as a great resource for the field moving forward. Okay, so other exciting work. Here's a summary of a paper that was, again, just published from Jamie Henderson and Krishna Shenoy's lab at Stanford, together with Lee Hochberg as part of the BrainGate consortium. And here they've designed a brain-computer interface that can literally turn the subject's thoughts into text. So they implanted 2 Utah arrays in the premotor cortex of a paralyzed patient. And what they did, the goal here was to provide this paralyzed individual the ability to communicate via texting, via typing. Now, previous methods were quite slow, on the order of 40 characters per minute, by having the subject move a cursor on a screen, again, with these implanted electrodes. But instead, what they did here was they asked the subject to imagine writing out the letters. And using a recurring neural network, they were able to learn how these patterns related to the actual imagining or writing of these letters, and turn this into a typed output. So it looks like this. And this, when I first saw this figure on the right, I thought, geez, they're doing gene transcriptomic analysis, but no, they are grouping these activity patterns according to the letter that the subject was imagining that he was writing, and they can turn this into text such that the patient could type 90 characters per minute with an accuracy of about 95%. So this rivals what most of us can do on a smartphone, typing out a text message. So this is really, really quite exciting. And it really paves the way for developing these neural prosthetic devices for locked-in patients or paralyzed patients, as well as really gives us insights about how information is being encoded in the motor cortex to generate these outputs. So this is all done in the lab, and it was done on one patient. And of course, one of the big goals of the BRAIN Initiative is to get these technologies out for use in patients at home. And so a study just published from Phil Starr's group in Nature Biotechnology is using adaptive deep brain stimulation together with wireless communication and deploying this in the home environment. So they have a fully embedded bidirectional electrode planted in subthalamic nucleus and motor cortex. And by fully embedded, this means that the communication is via wireless. There aren't wires coming out of the patient's head. And then these data stream to a tablet device and allows unrestricted movement of the patient in his or her own home environment. And this has allowed them to identify biomarkers of bradykinesia and dyskinesia, and to allow for developing a control signal for stimulation. So here you can see they can detect certain patterns of activity, which then trigger the device to stimulate to control these movement disorders. It has the potential of reducing side effects of open loop DBS, and it's really quite significant in moving DBS technology from the lab to home. And I'm sure we'll have many spirited debates about the neuroethical implications of these last two studies over the coming months. Okay, so COVID, what are we doing about COVID? I'll just finish up by summarizing some of NIH's efforts to address the COVID pandemic, which include the RADx program to develop at an accelerated timescale better and more widely deployable diagnostics. The ACTIVE program to develop vaccines. This, of course, has been on the front page of the news for quite a while, as well as research resources. Here's just a summary of a paper that was published from Dr. Avi Nath's group at the NINDS intramural. And very early on in the pandemic, I think some of you here had asked, what is the basis for this so-called COVID brain and these long haul effects that affect neurological function? And what Nath's group found is, looking at a number of postmortem brains, is that virus really is not detected in the brain per se, but it looks like that there is widespread evidence of inflammation and multifocal breakdown of the blood-brain barrier, leading to small infarcts and the like. So there's still a lot yet to learn, but I think all fingers are pointing toward inflammation and microvascular effects. And Walter is here; he can explain this a lot better than I can if you have questions. So there is an initiative at the NIH to address the post-acute sequelae of COVID infection, or PASC. It will be focusing on these different sets of issues and targets. The goal is to rapidly improve our understanding of the disease and to treat it ultimately, centering on several key scientific questions. And there are different components to this initiative. I can again refer you to the NIH website to cover this and for more information. And with that, I will stop and take any questions if we have time.
A fantastic presentation. In many ways, I wish I had reversed the order between the NIBIB Council, which was yesterday, and this talk. I had the opportunity to give them an update on brain, but you always get me up to date, and it was great to see the material. One thing that they did talk about, and maybe we could feed in this direction, they had an extensive presentation about RADx, which I'm sure you're very familiar with, which overall really seemed to have been quite a successful enterprise in terms of trying to take things from basic ideas and move them into the commercial realm very quickly and efficiently. And I'm wondering if you see any parallels to that, or any lessons that can be learned from that experience that could be applied in our space. Again, that's a big focus of what we're doing, but they seem to have really made some significant progress in terms of accelerating the process. I'll get a big check behind it.
Yes, Bruce, that's a great point. I've been talking with Bruce Trump.
ZipRecruiter helps me find qualified candidates really fast. 4 out of 5 employees who post on ZipRecruiter get a job.
You all mute. Great, thanks. Yeah, Bruce, that's a great point. I've been talking with Bruce Tromberg, director of NIBIB, about whether and how we could employ a similar mechanism as they have employed for the RADx, which basically is taking a very large number of ideas, I think in the thousands, and kind of funneling them into ones they can actually operationalize. And the key there is to look for goodness and not to try to find out which ones don't work, but just try to find out which ones do work. I think one of the keys to RADx's success was the large number of ideas coming in. This is being tried elsewhere. I'm very interested in looking at this because, frankly, I think there are certain areas where we're a little bit stuck in terms of making the next leap that we need. For example, spatial and temporal resolution in certain imaging modalities and other kinds of issues. So it could be a good way to complement what we're already doing in terms of basically providing opportunities for disruption. I think progress is going to go with strong increments, but we also need to find a way to allow for actually enable disruption. So it's certainly under consideration.
Great, thanks.
Elba, you had your hand up.
Yes, so impressive, John. Especially considering we've just gone through a lot of the COVID experience. I'm absolutely impressed with what you've said and really heartened by it. I did want to make two comments. I think that your new page is very, very important to create a sense of accessibility and approachability for the BRAIN program. So I landed on what you were doing on the page, and it was really, really good. I did want to mention that when you do the online course for business, if possible, to reach out to the minority business community. And I think you can advertise through the Government Minority Business Development Agency in the spirit of what we're trying to do here with DEI. But great
Yeah,
stuff.
thanks, Ella. Thank you very much. Somebody is taking notes here, right? Okay. Yeah, thank you.
Yes, we are, John.
Thanks. Of course you are. Other questions? I don't want to run us too late here, but
I
it's
think
always
Karen, maybe one more. Karen had her hand.
Karen, where are you?
Oh.
There you are.
I'm here. Thank you. That I also want to echo Elva's comments. What a great introduction to all the successes we've had this year with BRAIN, and the great, fantastic leadership. I wanted to ask about the commercializing innovation program, and some of the neuroethics community has been actively involved in trying to figure out how to bridge the public-private partnerships and how to bridge neuroethics across those areas. And I'm wondering if BRAIN has an intention to be maybe an exemplar in that space, and maybe thinking about neuroethics in that critical commercialization phase. Has that been discussed amongst the leadership?
We haven't discussed it explicitly, but I'm glad you bring it up. I mean, we're trying to weave the LC, right, the ethical, legal, societal impacts into everything we do, and not just have it be as an afterthought. And I think commercialization is certainly an issue that we need to be very aware of, not only in terms of who we try to draw in, but actually who we're trying to serve ultimately at the end of the day. So these are things that we will make a point to remember and see if there are explicit ways we can incorporate this. But we're really trying to weave this into the fabric of everything we're doing.
It's just an opportunity to also see neuroethics in action and have it be very actionable. So
yeah, absolutely.
I hope we do more with that.
Yep.